pleasure to introduce today's speaker, Professor Zongli Lin from University of Virginia. Zongli has been very active in the control research community for a long time. And he got his degree from Washington State University. And he is a fellow of IEEE, IFA, and several other societies. So he had really distinguished career. But I think you can see his bio, so I'm not going to get into that. I just want to point out two things. One thing maybe. He's going to be the general chair of APC 2028. So if you're planning your conference,
yeah, yes, it's going to be San Francisco. I just got a contract signed with a hotel 10 minutes ago. I just got email. Usually 5 years I have time. Yeah.
So anyway, in this high-gain world, he's going to talk about what we do with the low-gain feedback. Thank you. Thank you for coming.
Thank you, Jean. I should call you Professor Sun when I was a student, and Professor Jim as well. And it's great to be here. I feel like going to ACC or CDC here. So many control people here. And wherever I am, I saw maybe one or two in a day. So today I'm introducing this topic, low-gain feedback, which is a design method, basically, right? And I brought these two application areas. Low-gain feedback is not possibly particularly effective for dealing with saturation, nor dealing with time delay. I picked these two because I want to show some underlying inherent connections between these two classes of systems. So low-gain feedback does not deal with general problem of input saturation or input delay. But I just want to show through this, I saw that some interconnection between these two classes of systems, and both can use low-gain feedback. And this is the outline of my talk. First, I will briefly review the concept of high-gain feedback. I think a lot of control people are familiar with this design method. And then with high-gain feedback reviewed, then I will introduce low-gain feedback, right, the other extreme. And then I will review a few different methods for designing low-gain feedback. And then we'll talk about the application of this low-gain feedback for two classes of system. One is linear system in the presence of input saturation. And the design objective here is a concept called semi-global stabilization. So basically, we're trying to see how can we achieve a domain of attraction that is arbitrarily large, but bounded without hitting saturation, right? And the other class of system looking at, it will be linear system with input delay. And this input delay is arbitrarily long, meaning that it could be any delay arbitrarily long, but has to be bounded. So this is similarity already, right? One is the stability reason I want it to be as large as possible, but bounded. The other one is the time delay can be arbitrarily long, but has to be bounded. So I try to see through this and apply this low-gain feedback to these two type of problems, and like to show there might be some inherent connection between these two problems. And here's a brief review of high-gain feedback. We look at this linear system, right? So x dot equal to ax plus bu state space, and there's this disturbance here. D times w is disturbance, and the output z equal to c times x, right? And I assume the AB to be in this particular form, and this form is really not, it's without loss of generality, right? Because any controllable pairs can be transformed into this AB form, is that right? But once you construct a state transformation to bring the matrix A and B into this form, but we don't have freedom to also have special form of D and C here. So that's why D here, I have all numbers, D1 up to Dn, right? But here is by assumption, C here, I assume C, in general, C has to be all numbers everywhere. But here, I assume C has this special form. It's 1, 0, 0, 0, right? So it's special to have all these 0, but for 1, it's not really special. It's without loss generality, right? It's constant 1. And if you're familiar with this, if you look at the transfer function from U to Z here, the numerator is 1. Because the number in C matrix, C here is single input, is a vector, right? It's the coefficient of the numerator polynomials, right? Now, if the numerator polynomial is 1, that means I don't have any 0 here. So basically, actually, all I really need is not 0. I just need the system to be minimum phase. But if I assume there's no 0, there's always minimum phase. Is that right? So this is just for illustration. So C, special form of C here shows that this single input, single output system does not have any 0. And then high-gain feedback, what we do here is we take out the A and B matrix, and I design a feedback law. So this is a pole placement, right? A plus B times F. And these are the state feedback gain. So I place this closed loop pole to be at these locations. Lambda 1, lambda 2, lambda n, right? All of them have negative real parts. So without loss of generality, I'm assuming that the real part of lambda 1 being the most negative, and then and lambda n is the least negative, but still negative, right? And in this design, we can see here, the difference here, for A matrix, remember we have this number here, the last row here, A1, A2, An, right? And those correspond to the open loop poles, right? And in the high-gain feedback design, we assume this to be 0, meaning that we actually treat those numbers as uncertainties. We don't need those information to design high-gain feedback. And this is the nominal feedback. And the high-gain feedback is basically, we scale these coefficients, the feedback gains, F1, F2, up to Fn, in this particular form. It means the first number is scaled by 1 over epsilon to power n. And the next one is 1 over epsilon power n minus 1. And the last one is 1 over epsilon, right? So why I do this, you'll see this clearly. And then using this high-gain feedback, I substitute it into this, I get this closed loop system. Right? And now we want to see, okay, what's very special about this closed loop system? Basically, there's parameter here, epsilon, right? This we call a high-gain parameter. And we want to see how this look. We carry out a state transformation. Basically, we keep the first state as is. X1 is still X1 tilde, right? And the second state, I scale it down by epsilon. And the next state will be epsilon squared. And the last state will be epsilon n minus 1 to power. So I scale down all these states, right? And then I also making this fast time scale. So I define tau as T over epsilon. So in other words, the unit time unit will be different, right? Once we do that, you can carry out the closed loop system look like this now. Now I hope this is more clear now. Things that we see is we don't like will be disturbance here, is that right? All the W there are disturbance. And things we don't take into account in the design is A1, A2, An. These are the open loop parameters, right? But you can observe here, everything that we don't like, W and A here, all of them multiplied by, at least by epsilon, is that right? So that means what, if I make my epsilon small, so the effect of this disturbance and the effect of these open loop parameters will become small. So that's why high-gain feedback is robust against disturbance and also against the prime uncertainties, right? And that's basically, I think, the essence of high-gain feedback. And high-gain feedback, one observation is the gain itself will go to infinity. That's the reason I think they call it high-gain feedback. It's not that every gain that goes to infinity will be high-gain feedback. It has to be this special form. The first one is 1 over epsilon to the power of n, and the second feedback gain is 1 over epsilon n minus 1, and that way. So that's high-gain feedback is a good thing. And I mentioned, I was talking, I believe, with Peter this morning, right? High-gain feedback has problems being sensitive to to noise and things. But there's problem there, but still there's strength of high gain feedback. So now we want to see some property of high gain feedback. One property is so-called peaking, right? And I put a word here. Because the word peaking was created by Sussman and Kotovic. And I emphasize this is fast peaking because later you will see when we're doing low gain feedback, there will be peaking as well. And then we have what? Slow peaking. But why is fast peaking here? We look at a closed loop system, right? So we know that's the new state we define. And it scale, the first one doesn't scale, the second one scale by epsilon, and then keep scaling down, right? And just assume that disturbance equal to 0 here, no disturbance here. And the closed loop system can be written in this form. And remember, the initial state here is in the order of 1 here, because original initial state here, constant here, right? But once you scale it down, but the first one doesn't scale. So it's still in the order of 1, constant scale, no matter how epsilon becomes small, right? And the closed loop A metric here is in this form. And this form, I broke down this into 2 parts. The one part with when epsilon equal to 0. So this is the one by design, has eigenvalues lambda 1, lambda 2, lambda n, right? That's what we placed. And then this is a perturbation because of high gain feedback. But this term is order of epsilon, is that right? So continuity of eigenvalue shows that the closed loop eigenvalue would be lambda I, but plus order of epsilon. So if epsilon is small, then we know this under new state feedback, the eigenvalue is still in the neighborhood of lambda I, okay? And once we have that, then it's linear state space equation. We can get a solution, right? Remember, this is a new state, x tilde. A new state solution is transition metric times the initial condition. And remember that this initial condition in the order of 1 as well. And then transition metric, we know this has no epsilon there, basically, right? And so the solution here is in order of what? E to the power of lambda n times tau, right? But remember, tau equal to what? E divided by epsilon. So that's why the solution is 1 over epsilon times lambda n, right? So that means what? From here, we can see this new state. What do we see here? Remember, lambda has negative real parts, right? This state, as epsilon becomes small, this state, all of these states will convert to 0 fast as epsilon becomes smaller, right? But the starting point, initial condition, still in the order of 1. So no matter how small epsilon becomes, this initial condition doesn't become big, right? Now we want to go back to look at the original state. So the original state, x1, remember x1 and x1's tilde, they are the same. So x1 here still start with a constant and then decay to 0 very fast. Is that right? Now we look at x2 here. x2 tilde will scale down. Now we go back to x2, then it has to be scaled up by 1 over epsilon, right? So we have 1 over epsilon, then suddenly I have this, the transition become, the order here is 1 over epsilon, is that right? And this still goes to 0 very fast. But you imagine this, if I have a signal that starts with a constant point, 1's order, right? A constant, but it decays very fast after epsilon becomes small. But the maximum value will be very large, 1 over epsilon. So what kind of behavior could that be? You start with a constant, right? But you have to go down very fast, disappear very fast. But you know the maximum value will be very large, right? So the only way I think is you pick up like impulsive. You're starting from constant, you pick an impulsive level to level of 1 over epsilon, but go to 0 very fast. So that's why it's called picking, and I call it fast picking because it's disappear very fast. Now we look at the second state. Okay, we have picking. The first state, there's no picking. And the next state, the third state, then we have 1 over epsilon square, then pick even higher, right? And the last state here, you pick to the power of, the epsilon power of n minus 1. So that we have the highest picking, right? So the longer the chain of integrator is, the highest it peaks, right? And this is the peaking phenomena. But then we look at the control input here. The control input here that's the high gain feedback, right? And we know X1 is 1's order, and Xn is 1 over epsilon n minus 1 order. So all of these term is actually 1 over n to the power n minus 1 order. So high gain feedback, the control signal must be big, cannot be small, right? So this is what inherent in high gain feedback. I use a simulation to show here. Here I only show 2 integrators. In other words, n equal to 2. So it means what? The biggest you can pick is 1 over epsilon, right? Because n equal to 2. The left plot show here is epsilon equal to 0.01. The right plot, epsilon is 10 times smaller, 0.001. Now you can see here, the blue curve here is the first state. It doesn't peak. It converts to 0 very fast. And here the same, right? But the second state, which converts to 0 very fast, but peak to the large value. But these look like very similar. It doesn't look like converge very fast, but I'd like you to pay attention to the time scale here. Here is 0.1 second, and here is 0.02 second. So this is like 10 times faster than this, right? Or even more than that. And you look at the magnitude here. This look like very similar, but look at the scale here. It's minus 400, and this is the 40. So it's about 10 times smaller, right? But this is second order system. If we had a third order system, and the comparison of this would be 100 times. So this is the peaking phenomena. It's impulsive behavior. So high gain feedback, as we all know, there's some limitations, right? And the first limitation here is high gain feedback causes actuator to saturate. Remember, I just showed you control input will be in the order of 1 over epsilon to the power of n minus 1, right? So as gain become higher, then actuator is going to saturate. And second, the peaking phenomena I just point out. And this was first identified by Sussman and Peter Kotovic in the famous paper, 1993 transaction paper, in the context of nonlinear stabilization. Basically, it says that if the linear subsystem has these, then if there's a minimum phase nonlinear zero dynamic, this peaking will destroy the stability of the zero dynamic. So this is bad for high gain feedback. And also high gain feedback, or the high gain feedback, a lot of time, we need to place some assumption on the plant before we apply high gain feedback. One example would be this. You guys familiar with this? I know a lot of undergraduate classes does not teach this. Now I always teach this. This is locus, right? And you guys remember as gain K getting bigger, that's high gain, right? And all the branches of the loop loci approach to what? Open loop zeros, right? So as gain go to infinity, the poles will approach 0. So what does that mean? That means what? If the system is non-minimum phase, meaning that if there was one unstable 0, then one of the poles will go towards that one. So you lose closed loop stability, right? So high gain feedback is not generally applicable as either, right? It has to be for different applications that have different limitations. For example, stabilization, sometimes you need to have minimum phase property. Now let's given the good and bad things about high gain feedback. So it's still a motivator us to think about low gain feedback. So low gain feedback, I'm considering this state feedback, right? This pair A and B. And this pair AB is more special than the pair I used to consider for high gain feedback, right? Basically, these are all 0. So this means what? I'm assuming all the open loop poles are at origin, right? Channel of integrators. But actually, low gain feedback allows all the poles not have to be at the origin, could be anywhere on j omega axis. And we know you cannot have positive real part poles, because then as gain go to 0, then become open loops will not be stable, right? So the worst thing you can have is eigenvalue open loop poles to be on j omega axis. But here for simplicity, I first assume that all the eigenvalues of the A matrix are at origin. And the log feedback design, we start with the same design, assuming that I do pole placement F1, F2, Fn, and all of them place to these n locations, right? And also assume that lambda 1 has the most negative real parts, but all of them have negative real, right? Just without a lot of generality. And the low gain feedback is also scale, but this is just mirror image of high gain feedback, right? Remember high gain feedback, the first feedback gain was scaled to what? 1 over epsilon to the power n. Now I have what? Epsilon to the power n, right? And the last one is epsilon rather than 1 over epsilon. So this is very symmetric, right? And with this low gain feedback, and I will have a closed loop system like this. But here again, what is the behavior of this? So that's why we will carry out our powerful magic, right? The state transformation. So the gain here, that's what the gain here, right? And one property here, for sure, the gain will be in the order of epsilon. Remember, high gain feedback, the gain will be order of what? 1 over epsilon to the power of n, right? And here the gain is 1 over epsilon. Now, in order to see the closed loop system, I also carry out state transformation. The first state remain unchanged, but the second state, instead of scaling down, is scale up. Instead of epsilon times x2, now I have 1 over epsilon times x2, right? So I do this way, and then the closed loop system can be written this. Also time scale, instead of fast time scale t over epsilon, now I have epsilon times t, I call it tau. Then the closed loop system look like this. And nice thing about this is the right-hand side of this equation, I don't see any epsilon there, all right? It's very clean. At the left-hand side here, there's supposed to be 1 over epsilon, but 1 over epsilon become part of tau here. So the entire system, we make epsilon disappear. Right? And then we look at the closed loop system. Again, transition matrix, right? E to the power of ACL, right? Now ACL here, the initial condition here, instead of 1's order, now initial condition become large because I scale it up, right, the state. So initial condition is 1 over epsilon n minus 1. And the closed loop A matrix has nothing to do with lambda, epsilon now. So the eigenvalue of the closed loop system will be exactly at lambda I that we have chosen. Then we look at the solution. The solution we have in this form, right? And this is the same in this form. But remember, tau here is epsilon times t rather than 1 over epsilon times t. So then now you can see here, low gain feedback introduces what? Very slow time scale. The convergence will be very slow. That's what we lose, right? But the initial condition here is very large, right? 1 over to the epsilon n minus 1. Now we want to look at the state in original state. There's a peaking here. Then I call it slow peaking here. Slow peaking in n minus 1 state. The high gain feedback also we have n minus 1 state. The first state doesn't have peaking, right? And here we can see the first state again is 1 over n minus 1 here. And the second state multiplied by epsilon become n minus 2. And the last state, we have this maximum value, but scale down to epsilon n minus 1. So the last state, I don't have any peaking. So this is the opposite, right? High gain feedback, the first state has no peaking. But low gain feedback, the last state has no peaking. Now again, you can see here, the decay is very slow, very small, but initially it's also from constant value, right? But the maximum value is also large. So what happen now? We can take maximum value of these will occur at a very large time, right? Just take derivative, you will see that. So this shows that the state will peak to this large value, but very slowly. In what time order? Time order is 1 over epsilon order time, right? So this is low gain. Now the next question here, now we know all the state, original state, their peak value, the maximum value here is 1 over epsilon minus 1. That must be, right? Because all the states like that. But then if I look at, that's what we are really interested in, right? The gain is small, right? But the state is very large. Now, what's this? This is the control input, right? We want to see whether control input can be small or not. But if we are just looking at the state and gain, if we do a very rough estimate, here the state is 1 over epsilon n minus 1, and the feedback gain is epsilon. If you multiply these together, actually the order will be n minus 1, right? But indeed, it turned out actually, when you multiply these, it's epsilon's order. So that's a little bit surprising at the beginning when I discovered this. So then we will see how about control input, right? As I mentioned earlier, the state we have this, then now we look at the control here. The control, we can manipulate these numbers, come out. The control input here is in the order of epsilon. So that means what? We can avoid saturation by any given set of initial conditions. So that's semi-global stabilization, basically, right? And then more than that, if we take derivative of control, U here, if we take derivative of this will be also epsilon's order. So it means what? Under log-n feedback, not only will the magnitude of control signal be small, the derivative of the control signal will also be small. So that means what? You can avoid saturation in the magnitude and also in what? In rate. So this is the property. And so also example, the same second order system, epsilon equals 0.01, and this is 0.01, 0.001, 10 times smaller. Now you can see that you have the two states. The red one is the second state, which doesn't peak. The blue one is the first state that peaks, right? And now we can see this peaking, why I say slow peaking, look at time scale. This is 1,000 seconds, and this is 4,000 seconds. That means it takes a long time to peak to this value. And this value is about 10 times higher than this. Remember, this is 1 minus 120, and this is 1,200. So if I had 3 integrators, the third state, the difference of these would be 100, right? So this is log-n feedback, but log-n feedback also has peaking and slow peaking. But one nice thing about log-n feedback is the control magnitude for a given set of initial conditions can be made small. And the change rate of the control signal can also be made small. So this will be good for avoiding magnitude and rate saturation of actuators. And also time delay, the same thing, right? Think about it. If I have a control signal that changes very slowly, I don't care about delay, right? Yes.
Is this the same system as you showed for the high gain feedback?
Exactly, yeah. Yeah, and I use the same feedback gain, but just epsilon become 1 over epsilon. Yeah. So this is log-n feedback. And I saw this is the control signal, right? And remember, this is 0.06, and this is 6 times to 10 power minus 3. So there's no surprise there. And the original log-n feedback I mentioned earlier was just special class, right? All the open loop eigenvalue at the origin, right? Now, suppose I have eigenvalues that's general case, right? So AB is stabilizable. That means I could have eigenvalue that's negative already on the left, negative path. And all I require is eigenvalue to be less equal to 0. That means I could have j omega x's eigenvalues, right? And with this, now the design can be done in a similar way. Let me show you. First, I start with single input system. For single input system, all I need to do is I just using pole placement algorithm to move eigenvalues from the open loop eigenvalue to their left, all of them by epsilon. So all the eigenvalue become the eigenvalue minus epsilon. Is that right? And this is true for all eigenvalue that is on j omega axis. If an open loop eigenvalue is already stable, then I leave it alone, right? And that has these 3 properties. First, the gain will be in the order of epsilon, bounded by epsilon order, and transition metric will have this property. And this is the property that I showed earlier. Basically, the conversion will be fast in the order of epsilon, right? And second, the peak value would be to the power of epsilon to the power of r-1. And r here being the largest algebraic multiplicity. Remember, for a metric general, you could have multiple repeated eigenvalue on j omega axis, right? And some of them has bigger block and then others. And r is the biggest one. And the earlier example, we have one block eigenvalue at origin and r equal to n, right? So this is the order r-1. And how about this one? If I set I equal to 0, that means this factor is gone. So F time transition metric, that's the control input, right? It's bounded by epsilon. And then I put this in the middle here. That means what? The derivative of this control signal. So all of them bounded by epsilon. So this is general single input system, right? And the property I already mentioned that I already explained it. Now, if I have multiple input system and I carry out state and input transformation, and this can be done that all these metrics can be put in this form. And this is in the linear states, or some of the more advanced linear system textbook will have this transformation. So basically, I can block diagonalize all the A matrix, and A0 contains all the already stable eigenvalues. So I don't need to do anything. Now, each of these A1, B1, A2, B2, all of them controllable. That means I can be further transferred into this form. But this form, we already know how to carry out design, right? And the last column could be many columns here. These are redundant, so I don't need to do any control here. So we do this, then we design low-gain feedback as for each of these pair, AI, BI, for single input system, just power placement, right? And then I assemble the multiple input feedback gain, F1, F2, and up to FL. Suppose I have L blocks. And this is to move back to original coordinate, right? And this TI here also to move back to the original input space coordinate. And that's original design. And that design we call it, say, eigenstructure assignment, right? You assign eigenvalues and basically. And after that, there's a few methods that have been developed, but you get similar properties. The one is H2 AIE base, basically LQR Riccati equation, but you make Q metric to be epsilon dependent. And as Q go to 0, and then we have the similar property. About the same time, Andy Thiel come up with AIE, H infinity AIE based. And he was able to use H infinity to gain some additional robustness in the input channel. And more recently, I had a student that time in China, and then we worked together and come up with a minimal energy based control. And this one is nice in the sense that I can make a Q matrix to be, in other words, I set Q matrix equals 0. So that way, the Riccati equation will be reduced into a Lyapunov equation. And that way, we can get the discrete solution. But the property are all the same. And the low-gain feedback will be LQR type Riccati, LQR type feedback gain. So that feedback gain has this property. First, P epsilon goes to 0. And this property, actually, you look up 1970, Young Williams, 2 transaction paper already had that property, but he just didn't mention it in the context. And then this also has this property. And this property actually derives all these bounded state and all kind of property. They're equivalent, right? So the advantage and disadvantage here is that advantage of this is the AIE-based design will result in a Lyapunov function automatically because P is solved. But going backward, in the end, I was able to construct P for the AIE base, for the eigenstructure-based design by take a couple of pages to write it. So this one is nice. But on the other hand, the disadvantage is this P of epsilon here, the analytic solution in general cannot be obtained. So every time you change the epsilon, you have to resolve the Riccati equation. Yes?
The first property there, doesn't that require a minimum phase condition?
The what?
A minimum phase condition to hold.
And no here, because here we're dealing with state feedback, right?
Oh, sorry. Sure.
Yeah. All right. And so let's come back to the application. The first application here, the input saturation. Now suppose, so in nonlinear stabilization, I have this concept called semi-global stabilization. Basically means that if you give me a bounded set in the state space, I want to design a feedback law such that the closed loop system is locally asymptotically stable, but that set is included in the domain of attraction. And so it's not global stabilization, but it's quite close, right? Basically, the difference here is global stabilization, you have one feedback law that achieves global stabilization. But here, I can achieve a domain of attraction, not global, but can be arbitrarily large. But I have to use many feedback laws. In other words, you specify a reason, I have to come up with a new design, right? But here we use parameterization. So epsilon. So as you, for example, as I mentioned earlier, somebody specify a domain omega. So I can choose a feedback again, and this will be a function of epsilon. All I need to do is what? I make epsilon small enough so that the control input will never saturate. So it becomes linear system, and then it's globally stabilizable, right? And then any solution starting from here will converge. So that's the concept of semi-global stabilization. So low-gain feedback achieve semi-global stabilization. So that's what I mean by low-gain feedback is not necessarily the best way to deal with saturation because you avoid it. It could be very conservative, right? And the better one would be, I can still saturate, but I don't cause problem. That would be better. But it's a solution, right? That's one. And then this will be some simulation results. So here, this has two pairs of eigenvalues plus minus J. And I design low-gain feedback in this form, right? And you can see here, epsilon 0.1 and same initial condition. You can see for epsilon 0.1, the state will converge, but slowly, or peak. And the control magnitude will be small, right? Less than 1. But if you reduce the value of epsilon by a factor of 10, it still converges, but the peak value becomes 10 times bigger. And why is 10 times? Because remember, I have this R equal to 2, right? But it's slower. This is 100 seconds only to this point, right? And this is already converged, 80 seconds. And you look at control input here, this is value is 0.5 and this is 0.1 here. So control value also reduced. So this shows simulation. And then I also mentioned that that property can be used to prove something. Suppose actuator also has a rate saturation, meaning that the actuator responds also slowly. And then this is one of the model people use, right? And this is the magnitude saturation and this is rate saturation. I know I just say the magnitude equal to 1, Chris, right? Just make it simple, so no unit here. So I design feedback gain like this, and this is low-gain based. I also combine high-gain component here. And this we saw that this also achieve semi-global stabilization. So this is both magnitude and rate saturation. And one of the reasons I mentioned earlier, high-gain feedback has very good robustness property. But if I use low-gain feedback, I lose all those properties, right? And it turned out that these two can be combined. And how do I combine it? We call something we call low and high-gain feedback. And the condition is the same. AB is stabilizable and all the eigenvalue of this should be less equal to 0. By the way, this collateral system, Sussman and Sontag call this system ANCBC, stands for asymptotically now controllable with bounded controls. So basically, you can control to the 0. Now controllable meaning controlling to 0. With bounded control meaning the control is constrained. And asymptotically meaning that it will take infinite time to go to 0 because controllability is a finite time concept, right? So this is ANCBC system. And the low and high gain design has 2 steps. The first step, I will design low gain feedback like this. So once I have low gain feedback, then I will have construct a Lyapunov function through this equation P here, right? So if I use ARE, this P already given, right? With that, then I can take advantage of the infinite gain margin property of LQR, right? So basically, if I design a high gain part, the gain here is like this LQR, right? You add this term here, then the stability property will be retained. So in other words, if I use low gain feedback to achieve a certain domain of attraction, if I add a high gain in this form, that domain of attraction still remain. So you wouldn't shrink the domain of attraction. But then these high gain actions can be exploited to achieve properties. Is that right? So this is, you combine this to get low and high gain feedback. And I use this example to show. These are three integrators. And I have bounded uncertainty here, disturbance. I have uncertainty here, nonlinear uncertainty here. And the actuator has this property. This is both saturation and dead zone, right? And we know these are contradictory because to avoid the effect of dead zone, you need to gain to be large. To avoid effect of saturation, you want gain to be small. Sorry, Chris.
Yeah, no, that's fine. Now, maybe critically here, you haven't gotten to the delay part of
not yet,
things, right? So perhaps on slide 30, I mean, you were exploiting the infinite gain margin from LQR, but if any of those state measurements were subject to a little bit of sensor delay, then that's you would have practical issues implementing.
Exactly. Yeah. So in other words, this part doesn't carry to delay. That's why I mentioned earlier. There's some connections I like to bring up, and I think Michigan possibly the best place to pose question for, and we have so many people here. So this one look like contradictory, right? But it turned out because low and high gain work differently, right? And this is simulation result, and I choose epsilon to be small so that this set of initial condition work, and low to be large. And this is uncertainty, nonlinear uncertainty, and bounded disturbance. You can see all the states, or in the end, converge to a small neighborhood of 0. And then the contour is like this. This basically is saturation and dead zone, right? So like a bang-bang contour type. So by combining low and high gain, we take advantage of both low gain to avoid saturation and high gain to avoid dead zone and uncertainty. So these are the property. And another little one, I think I like it. It's called composite nonlinear feedback. And that's when I was visiting the Air Force lab many years ago. And they asked me to design some controllers, and I come up with this for the fighter jet, right? It's second order simplified equation here. The idea here is, suppose I have this composite nonlinear feedback, basically low and high gain feedback. And I design of low gain feedback to make its linear feedback, right? And the low gain feedback will make what? Second order system. I make the density ratio to be very small. So what does that mean? That means the system will respond very fast, but very large overshoot, right? But then the high gain feedback, we know high gain feedback could be any high gain feedback you add will work. Then we say we schedule the high gain feedback state dependent. So as the state getting closer to the steady state, I increase the gain. What happens is you can prove that as gain get bigger, the density ratio become large. So that means what? Your control effect will be, you start with very small density ratio and will shoot up very fast. But before you overshoot, you increase the gain. So that it's like a breaking of the system, right? And the density ratio become large and you slow it down. And I'll show you this feedback. Okay. So first I do low gain feedback. And this design, and we know we design G here so that we assume the DC gain to be 1, so we can track the signal. Is that right? And then the high gain feedback, we will design, I think I skipped, maybe I skip. Okay, the second step, I design high gain feedback. Remember this high gain feedback low here. Here I make low to be state dependent. So if the output and R are getting very close, then I increase the gain. And that you can prove that it increased the damping ratio. So you add these two together, and this gain, I will choose this property, right? When the output is close, then I make this to be large. When the output is far away, I make it small. So then you have this property, and I use this example I took out from they give to me from the Alpha's lab. This is F16, I never seen 16, but from the classic book, Braylock book, and the second order system. And we come up with two designs. The first design, I choose F and G this way, and G this way so that the DC gain equal to 1, right? This way, choose the damping ratio 0.7, which is pretty big damping ratio. And then I combine this, I get, it's called composite nonlinear feedback and two gains. And I choose this gain to be this function. And you can see that's the response. The dotted line here is the reference, right? So the output here is the pitch rate of the airplane. And the dashed line here is what? If I let low gain feedback continue, and this will be linear feedback. You have this good, this is the 0.7 damping ratio response, right? And this is the 0.7 damping ratios overshoot, is that right? Then and that's how you get this, right? This linear response. But if I add the nonlinear component, high gain component to it, then I get the same, almost the same rise time, right? But then I control the what? The overshoot. So this become, you avoid this overshoot here. So you get better response. But you can do a little bit more extreme. If I set this F to be here, then the damping ratio 0.4, then we know smaller damping ratio means what? The response will be faster and the overshoot will be larger, is that right? So, but then I use high gain to control it. Now you can see. So if I leave the low gain feedback to continue, then it will be like this fast response, but very large damping ratio, right? But if I add high gain feedback, almost I cut this and this solid line here. So this is, and of course in the paper, we also take saturation into consideration. So that's the first application, the application of input saturation. So the second application here, that's one I draw attention to is the delay. The input has delay. Now I assume that this is a positive delay, right? And I don't need to explain when delay happens, right? So basically, you take time to compute the control and transmit the control signal. So one of the effective methods for counteracting delay is so-called predictor feedback, right? So the idea of predictor feedback is very simple. First design, you assume delay equal to 0, right? Then you design probe placement F there, right? So if there's no delay, then the closed loop eigenvalue will be A plus BF, stable, no problem, right? Now with delay, now the question is, once you have delay, things get lost, right? Then somebody being smart said, well, I can predict the state, right? So basically, predict state, I use, instead of FXT, I use XT plus tau, is that right? Then when you implement it, then the closed loop system will be like this, no delay. So this is predictor feedback. So you predict the state, so to cancel the delay, right? Now the question is, how do you predict? Then people say, well, and that's easy because I have linear system. I can solve the equation to get the state, right? So assuming that we can solve that, then the state at t plus tau actually can be written in this form. But the little problem here is that this state here, in order to determine the state at t plus tau, I need the history of the input before that time, right? But remember, we are using this predict state to compute the input, right? But you need input there. So this becomes like what? Chicken and egg problem, right? And this basically, in other words, the feedback end, when we implement it, will be in this form. And this is distributed control law, infinite dimensional. And then people, in implementation, I think most of the time, no problem. You can implement numerical integrator here, right, to do it. I think a few years ago, somebody came up with the example. No matter how accurate your numerical integration could be, it could still cause instability. So the motivation we had here is delay feedback. You have this is not good, right? Now, the idea here, you look at this point in two ways. Right? One is I mentioned earlier, under low gain feedback, if the control change, the change of speed of UT, the control input is very slow, then you are more robust to delay, right? Extreme case, I have constant input, I don't care, you're delayed, right? So that's the one way of thinking that. Now the question is, low gain feedback can do it, right? But then low gain feedback requires the open loop system eigenvalue to be on the closed left half plane. And that's identical to what? To low gain feedback we apply for input saturation. So these I see the connections, right? I use same tool for two different problems, but it had to work for the same class of system. And another way to look at this is this. If I look at this, and this is epsilon order, right? And if I use low gain feedback here, this is also epsilon order. Now, if epsilon order times epsilon order, this term becomes epsilon square order, but this term is epsilon. So that means this epsilon square order possibly can be dropped. And we saw indeed is the case. And this was in earlier paper. So we get this, and we call it truncated predictor feedback. Basically, we throw out the distributed term, right? And then furthermore, we saw that actually, if all the eigenvalue, if I don't have any eigenvalue on non-zero but j omega axis, so meaning that if there's no oscillation, then in that case, I don't even need this term there. And implication of this, that means what is more robust to the delay. So in that case, and just low gain feedback will work. And I use one example to show this, and this again, the same example, fourth order I saw earlier. And I will get a feedback gain like this. And this is the simulation, right? So 0.1 second, I have to choose epsilon to be 0.5, and that's the response. But if it's a 2 second delay, then this epsilon need to be smaller. So in other words, the larger the delay is, this epsilon has to be smaller. But then the response becomes slower. And another example is this example. This I have two channel integrator here with all eigenvalues, but there's two inputs, because in order to be controllable, I have two blocks, then at least I need two input, right? And because I don't have j omega, non-zero j omega axis forwards, I don't need this transition matrix here. So I just low gain feedback. Then you can see that it's actually same thing, right? If it's 0.1 second delay, epsilon can be moderate, 0.5. If it's 2 seconds, then epsilon has to be very slow. And then of course, then the response becomes slower. So it's always a trade-off there. So that's the conclusion. As I mentioned earlier, I introduced this low gain feedback to see the connection between these two classes of problems, right? One is delay and the other one is saturation. But this low gain feedback deal with same class of systems, so-called ANCPC, right? Asymptotically now controllable with bounded control systems. Now the question here is, if the system is more general, and low gain feedback wouldn't work for this, but is there any connections for this? Maybe some tools that was developed for saturation for general system can be used to deal with delay for general system, or the other way around, because the delays literature has so many tools, right? Maybe I can use that. And the more I think about it, I think the more it makes sense, because saturation is almost like delay, because when you hit saturation, you just like if you want to speed up, you're driving uphill, right? And you want to speed up, you don't have enough power to do it, right? But it takes longer. In the end, you can continue to do it. But how I do it, I don't know. All right, that's all I have. And you have any questions, and I'll be happy to answer. Yes.
Is there somewhere we can find a list of the papers that you were talking about in this presentation?
Yes, yeah. I can send you the slides, and then if certain paper you couldn't find it, just let me know about that.
Do you have citations in these slides for your papers?
Some of them mine, some others, yeah. But let me know, I will email you.
I think the slides will end up online.
Okay, then just tell me which slide, which citation I was pointing out to you.
So,
yes.
To me, the obvious question is how much of this extends to output feedback?
How much
of this extends to an output feedback version of this? Most of your results were for state feedback. Can you do something?
And all these results I have talked about, all of them have feedback version of it. One reason is because, for example, in the saturation part, right? Because I have F time X, right? And F is no problem, F is small, right? The problem is X could be very large, the slow picking, is that right? But if I use a standard observer, then X become X plus E, is that right? But E, I don't use low gain, I don't use high gain, it's bounded. So then FE is always small. Does it make sense?
If you do an analogous kind of high gain,
because I don't need to do that, right? I just use regular observer, Lomberger observer.
There's not some kind of way you pull the same trick with the observer design that you're pulling to the control design somehow.
You can do it separately, right? Basically, suppose I have one magnitude for input, right? So I can reserve 0.9 for state feedback, Fx, right? Then I reserve F1 for Fe, right? But F is low gain, I can make gain small, but makes sense? Yeah. And the same thing for delay as well.
Can I follow on his question? So
yeah.
You have input saturation at the plant. You're doing this low gain, high gain.
Right.
What's the analog in the estimation problem? If I only want to build an estimator and the sensor saturates.
Okay.
Like low gain, high gain observer problem.
That's much, we try. I did prove a paper, a simple result for semi-global stabilization and output feedback, right? Basically sensor feedback. What we proved that was I was able to achieve semi-global stabilization if all the zeros are on the closed left half plane. So this is like kind of dual, right? For state feedback, you want the open loop pole to be closed left half plane. But for that, I need all the zeros to be closed left half plane. And the idea is I will cause the system to oscillate. Once it oscillates inside the linear region, then the observer will work a little bit, right? And then it work out. But I can only do it for single input system. And over the time, I had some of my students tried, and none of them was able to go further. And one reason is observer output or sensor feedback is much harder to deal with. Because the input feedback, you have Fx to be saturated, but I have a choice to design F, right? But for observer, the sensor saturation, you don't have a control of the sensor, right?
So Zongli, related,
yeah.
I think like Hassan Kalia did this high gain observer to avoid peaking.
They use, he used saturation, right? And then, in other words, if you use high gain observer like a high gain feedback also has peaking, is that right? Then this peaking will show up in the FE, in the E part. And what clever thing that Hasan-Khalil did was he saturated intentionally control input. So FX, there's no saturation, is that right? But FE, that part, has saturation. But he saturated that signal so that, but this FE saturation peak disappear very fast. So he cut off all this saturation, the peaking, so that wouldn't affect the overall stability, yeah. So he actually introduced saturation to cut out the peaking, yeah.
Any other questions? If not, thank you again.
Thank you.
Holding that he shouldn't be titled.
There's a question online.
Oh, yeah, I forgot. Do we have anybody online?
Sorry, guys. They already left. Oh, there's a question online.
Hello.
They probably left. Sorry about that. My fault.
That's okay. They will email me possibly.
Who is that?
Zhexian Liu. I don't know.
Yeah.
From Michigan.
Yeah.
Then you can ask him to contact me. But the answer is no.
Okay. All right. So we can end here.
Yeah, how do I?
Stop sharing and